All right, we got an absolute freaking banger of a section today, and it's the trace-determinant plane. So, just sort of having lunch. But this section is like the convergence of everything we've been learning about differential equation systems for the past freaking 6 weeks coming together, particularly linear. It has to be linear. Okay. All right. I'm done. I'm going to put these in the fridge, and then we're going to get locked in. Okay, so what is this section all about? In the previous sections, we've encountered a number of different types of linear systems. All right. In the previous sections, we've encountered a number of different types of linear systems of differential equations. At this point, it may seem that there are many different possibilities for these systems, each with its own characteristics. In order to put all of these examples into perspective, it is useful to pause and review the big picture. One way to summarize is to make a table. As we've seen, the behavior of a linear system is governed by the eigenvalues and the eigenvectors of the system. So our table should include the following: the name of the system, the eigenvalue conditions, and a couple of phase portraits. For example, we could begin to construct this table in 3.1. This list is by no means complete. In fact, one exercise at the end of this section is to compile a complete table. There are 8 other entries. Oh, shoot. As is so often the case in mathematics, it is helpful to view information in several different ways. Since we are looking at the big picture, why not try to summarize the different behaviors for the linear systems in a big picture rather than a table? One such picture is called the trace-determinant plane. Bro, trace-determinant plane is so cool. Okay. So in these cases, we have real eigenvalues. We got a saddle, a sink, and a source. Then here we got conjugate pairs, right? So for this whole thing, we're talking about linear systems with real coefficient matrices. Spiral sink, spiral source, center. All right, trace and determinant. Suppose we begin with a linear system, y prime is equal to ay, where a is the matrix ABCD. Its characteristic polynomial is going to be lambda squared minus a plus d lambda plus ad minus bc. The quantity ad is called the trace, is the sum of the diagonal. and AD minus BC is the determinant of A. So the characteristic polynomial can be written more succinctly as lambda squared minus T lambda plus D, where T is the trace and D is the determinant. So if A is equal to 1, 2, 3, 4, then we get this characteristic polynomial with this trace and this determinant. Remember that the coefficient of the lambda term is minus T. It is a common mistake to put this minus sign in the wrong place or even forget it entirely. Okay. Since the characteristic polynomial of A plus, okay, here's how you remember. This is one of those things. Is you just rederive this. You just do this again. It's so easy. This is actually what you do instead, and then you just will never forget the formula. It is a common mistake. Okay, since the characteristic polynomial depends only on T and D, it follows that the eigenvalues of A depend only on T and D. If we solve the characteristic polynomial, we get this. From this formula, we see immediately that the eigenvalues of A are complex if T squared minus 4D is less than 0, and they're repeated if it equals 0. They are real and distinct if the quantity, the discriminant is greater than 0. Remember, the discriminant is just this quantity, T squared minus 4D. We can now begin to paint the big picture for linear systems by examining the trace-determinant plane. We draw the t-axis horizontally and the d-axis vertically. Then we draw the curve t squared minus 4d equal to 0, or d is equal to t squared over 4. It's a parabola opening upward in the plane. We call it the repeated root parabola. Above this parabola, t squared minus 4d is less than 0, and below it, t squared minus 4d is greater than 0. To use this picture, we first compute t and d for a given matrix, then locate it on the point in the plane. We can then immediately read off whether the eigenvalues are real, repeated, or complex, depending on the location of TD relative to the repeated root parabola. We can actually do much more with the trace-determinant plane. For example, if t squared minus 4d is less than 0, the point lies above the repeated root parabola. Then we know that if the eigenvalues are complex, then their real part is t over 2. We have a spiral sink if t is less than 0. Wait, we have a sink. Wait, hold on. In this, we get... Oh, yeah. Right. You got to be careful with this. This is a positive. All right, so... We have a spiral sink if t is less than 0, a spiral source if t is greater than 0, and a center if t is equal to 0. If TD lies to the left of the d-axis, the corresponding system is a sink. Wait. Left is a sink. To the right is a source. And a center if the trace is 0. Dude, that's so cool. That's so cool. I remember seeing this like so long ago, and it's just like the coolest thing ever. All right, real eigenvalues. We can also distinguish different regions in the trace-determinant plane where the linear system has real and distinct eigenvalues. Okay, in this case, TD lies in the below the repeated root parabola. However, if t squared is minus 4d is greater than 0, then the real eigenvalues are this. If t is greater than 0, oh yeah, okay. If t is greater than 0, then we have a plus plus a plus. So to figure out what type the system is in terms of like saddle or sink or source, we have to figure out what the sign of t minus discriminant square root discriminant is. Actually, okay, so the discriminant is without the square root. If d is equal to 0, then this eigenvalue is 0. We should make one of those decision trees, you know? D is equal to 0, then this eigenvalue is 0. Because you're going to get t minus t. So we have one positive and one negative, and one 0 eigenvalue. If d is greater than 0, then t squared minus 4d is less than t squared. Since we are considering the case where t is greater than 0, we have okay, so then we have a source. Great. On the other hand, t is greater than 0, but d is less than 0, then this is greater than, so we have a saddle. In this case, the system has one positive and one negative eigenvalue, so the origin is a saddle. Oh, we need to think about that too. Oh man. Let's if D's equals nuts. Profound. I gotta think about that one. If D's equals nuts. I don't think mathematics is ready for that. If D's equals nuts. Okay, so in the case that t is less than 0, this is going to be positive, and this could be positive or negative. So if d is greater than 0, wait, why do we get two negative eigenvalues? We have t plus or minus the square root of t squared minus 4d over 2. If t is less than 0, oh, and this is greater than 0. Oh, okay. Okay, so if t is less than 0 and t squared minus 4d is greater than 0. So we still have real eigenvalues. However, if square root of t squared minus 4d is greater than t, then we get one positive and one negative. So if it's 0, yeah, okay, all right. So it's the same as above, it's just flipped. Finally, along the repeated root parabola, we have repeated eigenvalues. Because that is where, yeah. So if t is less than 0, both eigenvalues are negative. Because, well, why would you say both? There's only one. Wait, in this case, so above this is where 4d, so above, so you plot t squared is equal to 4d. And so if 4d is greater than t squared, then complex. So you get to the spirals on top. But here, in this case, t is negative. So if we have t less than 0 and t squared is greater than 4d, then we're going to have t plus or minus something that is positive. It's positive and it's going to be less than t squared minus 4d is going to be less than t squared. So then t minus the discriminant. Okay. Okay, if the determinant is negative, we automatically get... Wait, if the determinant is negative, let's say t is equal to 0, then we get 0 plus or minus the square root of minus 4d. Then we're going to get one positive and one negative eigenvalue. But shouldn't they have arrows here? So if the trace is... I gotta think about that. All right, the parameter plane. The trace determinant plane is just an example of a parameter plane. The entries of the matrix A are parameters that we can adjust. When these entries change, the trace and determinant of the matrix also change, and our point moves around in the parameter plane. As this point enters the various regions in the trace determinant plane, we should envision the corresponding phase portraits changing accordingly. Right. The trace determinant plane is very much different from previous pictures we have drawn. It is a picture of a classification scheme of the behavior of all possible solutions to linear systems. We must emphasize that the trace determinant plane does not give complete information about the linear system at hand. For instance, along the repeated root parabola, we have repeated eigenvalues, but we cannot determine whether we have one or many linearly independent eigenvectors. In order to make that distinction, we must actually calculate the eigenvectors. Right, so this doesn't tell you the geometric multiplicity on the repeated root parabola. Similarly, we cannot determine the direction in which the solutions wind about For example, A and B have trace 0 and determinant 1, but solutions of the system wind around. So they're here. They're a center. They're both centers. Wind around the origin in the clockwise direction. And B is in the counterclockwise direction. Okay? All right, the harmonic oscillator. We can also paint the same picture for the harmonic oscillator. Recall that this second order equation is given by where m is greater than 0 is the mass, k is greater than 0 is the spring constant, and b greater than or equal to 0 is the damping coefficient. Okay, we get this system, and we calculate the trace and the determinant. We plot right. Did we have that on there? Yeah, these are good. Since m and k are positive. Wait. And b is non-negative. We are restricted to 1/4 of the picture for general linear systems. I'm gonna go get some socks. It's cold today, man. It's cold, bro. If the damping is 0, then the trace is 0, which means that it's going to oscillate forever. because it's a center. All right, navigating the trace-determinant plane. One of the best uses of the trace-determinant plane is in the study of linear systems that depend on parameters. As the parameters change, so do the trace and determinant of the matrix. Consequently, the phase portrait for the system also changes. Usually, small changes in the parameters do not affect the qualitative behavior of the system very much. For example, a spiral sink remains a spiral sink and a saddle remains a saddle. Of course, the eigenvalues and eigenvectors change as we vary the parameters, but the basic behavior of solution remains more or less the same. The critical loci, the critical loci. There are, however, certain exceptions to this scenario. For example, suppose that a change in parameters forces the point to cross the positive d axis from left to right. The corresponding linear system is changed from a spiral sink to a center and then immediately thereafter to a spiral source. Instead of all solutions tending to the equilibrium point at 0, 0, suddenly we have a center, and then all of the equilibrium solutions tend to infinity. The family of linear systems has encountered a bifurcation. The trace-determinant plane provides us with a chart of those locations where we can expect significant changes in the phase portrait. There are 3 such critical loci. I'm going to write that down. The first one is if TD crosses this line as our parameters vary, our system moves from a saddle to a sink, a source, or a center. As long as D is negative, as long as the determinant is negative, I gotta think about that second one, but that's okay. All right. The third is the repeated root parabola. Yes, the system remains unchanged unless you cross the fence. Okay, a one-parameter family of linear systems. Consider the one-parameter family of linear systems y prime is equal to ay, where a is equal to this, which depends on the parameter a. As a varies, the determinant of this matrix is 2a, but the trace is always minus 2. Oh, yeah, dude, this is fun. I like this. So we're moving on a line of t. Oh, wait. We're moving on a line of d. So we get 3 possible behaviors of systems. All right, let's get to the exercises, man. All right, so I guess one thing to note that depending on where we place A, we can make, depending on what A, the big A is, we can make it so that the trace, the determinant, or both, or neither depends on A. If A is here and this was 0, and this was 1, I think. Okay, so bifurcation from sync to spiral sync. Let's investigate how the bifurcation from sync to spiral sync occurs. So let's all right, so we have a sync, and we're going to go up to here and have a spiral sync. So we're increasing the determinant until we cross this, what is it called? The repeated root parabola. Get some water. That's good stuff. All right. We need to first compute the eigenvalues and eigenvectors of the system. Of course, these quantities depend on A. Since the characteristic polynomial is lambda squared plus 2 lambda plus 2A, because okay. The eigenvalues are going to be these, like we just saw. As deduced above, if A is greater than 1/2, then we have complex eigenvalues with negative real part, which means spiral sync. If A is less than 1/2, then we have two real eigenvalues, and this is going to be less than 1, so both are negative. Hence, the origin is a sink with two straight line solutions. Figure 3.51. Okay, yeah, you see we got this one, and we got this one. If we compute the eigenvectors for the eigenvalue lambda is equal to -1 plus 1 minus, we find they lie along the line. This I would like to verify, but not right now. Similarly, the eigenvectors corresponding to the eigenvalue lambda is equal to -1 minus. Oh, cool. Note that both of these lines tend to, the slopes of both of these lines tend to 2 as a approaches 1/2. That is, our two straight line solutions merge to produce a single straight line solution. Because we're going to get t squared is 4. And we get 4 times 1 is 4. So then the determinant is equal to the, or t squared equals 4d. Eigenvalue repeated. This system has a single line of eigenvectors that lie along the line y equals 2x. Let's see, how much more do we have with this? Oh, good. We're almost done. Sometimes I feel like they belabor the points a little bit. It's like, you don't have to go, I don't know. You don't have to say the same thing over and over again. Okay, when the perimeter crosses it, finally, the origin becomes a spiral sink. The one thing that I wish they would have shown is the case where the trace and the determinant, bifurcations when the trace and the determinant both depend on A. Okay. Let's read through the exercises and decide which ones we want to do. All right, construct a table of the possible linear systems as follows. The first column contains the type of system. Whoa. Really? 14 cases? All right. I mean, I guess we kind of should do one. 14's a lot, though. There seems like an interesting combinatorial pattern. I wonder... I'm actually excited to get to 3.8. I feel like 3.8 is going to be really cool. Okay. All right, problem 2. All right, in exercise 2.7, we consider the one parameter families of linear systems depending on the parameter A. Each family therefore determines a curve. Is it a curve? Or is it a line? I was thinking it's a line. All right, we're going to have to do a lot of these because these are really interesting. Yeah, these are good. I like these. Identify the values of A where the type of... Okay, these are the bifurcation values of A. Great. Yeah, so we'll do one. We'll do the odd ones. I like the odd ones because then we can check the answer at the back of the book. All right, so this is section 3.7, right? DE 3.7. So we're going to do exercises 1, 3, 5, 7. Maybe we'll do more, but I mean, consider the 2-parameter family of systems in the AB plane. Oh, that's cool. That's cool. We got to do 8. So the trace here is going to be 2a, and the determinant's going to be a squared minus b squared. All right, we'll do 9. Consider the 2-parameter family of linear systems. So this one's going to be a squared plus b squared for the determinant, and 2a for the... I can definitely see one of these problems on our quiz. All right, we'll look at 10, but I don't know if we need to do 10 if we do 9. Okay, in exercises 11 through 13, we consider the equation of the damped harmonic oscillator. In each exercise, we fix 2 values of these 3 parameters and obtain a 1-parameter family. Rewrite the 1-parameter family as a 1-parameter family of linear systems. Wait, what? Oh, yeah, just write it as a system. Just convert it to first order. Draw the curve in the trace-determinant plane obtained by varying the parameter, and in a brief essay, discuss the different types of behavior exhibited. All right, we can do 11. Hey, what's up, no name? 13. Oh, that's it. Oh, this is a short section. All right, we'll do 13. All right, so we got a lot of work to do. All right, so this problem is going to be tough. Problem 1. We're going to make a table. All right, let me see. How many did they give us? Let's copy those down. Or let's just at least count them and then we'll do them ourselves. But so they give us 6, but then there's 8 more. All right, so I think we can start off with these 3 because I think that these 3 are completely characterized. I don't think that there's any other complex ones. So we get spiral, sink, spiral source, and center. Then we're going to get saddle, sink, and source. But now I want the case where we have a repeated sink, repeated source, then 0 sink, 0 source. How many is that? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Both 0. 11. What else can there be? I'm missing 3. Is this further maths? I don't even know what that means. Okay. So we have spiral sink, spiral source, center, saddle, sink, source, repeated sink, repeated source. So let me write down the conditions. So spiral sink is all right. So this is going to be lambda is equal to a plus minus bi, with a is less than 0. It's going to be a greater than 0, then a equal to 0. All right, saddle is this one. Lambda 1 is less than 0, and then lambda 2 is greater than 0. A sink is lambda 1 is less than lambda 2 is less than 0. A source is 0 is less than lambda 1 is less than lambda 2. Okay, a repeated sink is 0 is less than lambda, lambda lambda 1 equals lambda 2 is less than 0, then a repeated source is when 0 is less than lambda 1, which is equal to lambda 2. A zero sink is when we have lambda 1 equals 0 and lambda 2 is less than 0. And the zero sink case is where you have a line of equilibrium points because you have a non-trivial null space. Oh, I'm following the book Linear Algebra and its Application. Or wait, sorry. Differential Equations Blanchard. It's in the title of the book, or in the title of my video. It's at the end there. Sorry, I'm also covering a linear algebra book and I'm getting confused. All right. So the zero source case, so these are not filled in here. The zero source is going to be where lambda 1 equals 0 and lambda 2 is greater than 0. And then we have the both 0 case, lambda 1 is equal to 0 is equal to lambda 2. All right, now I'm willing to, let's look at this plot again. Where's the actual plot? What am I missing here? I got the repeated roots here. We got the saddle. We got this 1, 2, 3, 4, 5, 6, 7, 8. And then when they're both 0, so we did the both 0 case. We're missing 3 of them. I'm going to go to the answers. They probably don't even provide the... Are discussed in 3.5. We did 3.5, but I don't remember. So we got the repeated eigenvalues. Oh, you know what we didn't get? Wait, actually, hold on. Wait, no, this is a repeated... Wait a minute. No, I think we did that one. Oh, you know what we didn't do, though? No, we did that one. Because that would just be a source and a sink. We did this one. This is where 0 is an eigenvalue. All right, I'm going to ask ChatGPT. I think that... Don't forget the double eigenvalue and 0 eigenvalue cases. I did... Those were easy. I got those. Trace-Determinant plane and 2x2 systems. What's up? What book are you following? Think about Hirsch Smale. My high? No. What's going on, guys? Nose hair? Bro, who said nose hair? That's funny. All right, so I got 11 of them. I didn't get the last 3. I don't know how there are 14 of them. Okay, so so wait, 1, 2, 3, 4, 5, 6, 7, 8, 10, 11. Spiral, sink, spiral, source, center, sink, or center, saddle, sink, source, repeated eigenval, sink, repeated, source, 0 plus sink, 0 plus source, and both eigenvals 0. But that only gives me 11 out of 14. Some books will expand on the classification. Okay. Saddle. Real distinct eigenvalues of the same sign. Okay. So sink and source. Complex conjugate. So we get spiral sink, center, and spiral source. All right, so we got the first most common 6. Then we got the repeated eigenvalues. Okay, star sink is where okay, these are the repeated real eigenvalues where oh. Okay, so we got this one. Double 0. So we got this one. What's the difference here? So this would be something with like a single entry. Or it doesn't have to be a single. I think it does have to be a single entry. How else could you get the determinant 0? Okay, wait, let's go through these. So repeated Bro, what the fuck is further maths? I think you're missing the dots for the 0 eigenvalues. No, all of the ones that I'm missing are in here, in the repeated roots. So we have, all right, let me just remake my table. So a star sink is where D is, so this is star sink. D is equal to 0, discriminant is greater than 0, and the trace is less than 0. So why does this mean that we have 2 genuine eigenvectors for repeated roots? So this would be like Oh, this is a star sync. This is like a diagonal. This is like a scalar multiple. Okay, yeah. So we got the star sync. So this is like every vector is an eigenvector, right? So wait, let's go to star sync. Yeah, so that's what I was saying. And then an improper node sync. So then improper node sync. What does that mean? Oh, A equals lambda I. A does not equal lambda I. So this is where we have a discriminant greater than 0, a determinant equal to 0. So what is that behavior? So this would be like -2, 0, 0, -2. And then this one would be -2, 1, 0, -2. Okay, star source. Okay, star source is easy. So these two I missed out on. Improper node source, I guess, and so what do those look like? These are the ones. So wait, but there were 3 that I missed out on. I missed out on this one, and this one, nilpotent node. This is 12, 13, and then 14 is nilpotent node. What does nilpotent mean? It means that it has a non-zero null space or something? Oh no, nilpotent means, oh, interesting. Wait, that's so weird. Nilpotent means there exists a positive integer n called the index or the degree where x to the n equals 0. That's wild. I didn't know about that. Hold on. Some books call it dots because 0 eigenvalue has 2 types. Yeah, right. I know what you're talking about. Yeah, drawing a line. Yeah, it approaches the line. Nilpotent means it ends up annihilating to, yeah. Okay, so wait, we're doing this. Oh wait, I'm here. Use Python to make phase portraits for direction fields for 8, 10, and 12. See, this is a great table. I like this table, man. What? So improper node sync. Improper node sync is where you have only one eigenvector, right? So the geometric multiplicity of the eigenvector is Draw all of the eigenvectors as a line on each two. They may. And then I want to know. Okay, so these are just some trajectories, right? Yeah. So okay. So these cases. This is actually. Oh yeah, this case, nilpotent node. Bro, why is it being so dumb? Yeah, so basically what this means is that all trajectories, so in both of these cases, the eigenvector is actually in the null space of the matrix, so that means that it's already at equilibrium. However, if you're not on that line, then all trajectories eventually end up being tangent to the line. And here they end up approaching the origin and being tangent, and here they go to infinity and end up being tangent. And then this one is just already tangent. But you have these flows. So that's perfect. That's good. Can you do this for all 14 cases? Bro, ChatGPT is fucking awesome, man. Bro, I'm gonna. Oh, this is so good. Okay, so saddle, right? Because if you're here and you get kicked off, you're gonna go over to infinity. But otherwise, if you're on this straight line, you go down to 0. Stable node, that's perfect. Unstable node, you go away in both directions. Spiral sync, that one's easy. Spiral source, that one's easy. Center, that one's dope. Star sync. Okay, so star sync was kind of the one that I missed, actually. Yeah, so star sync was one of the ones I missed. This one I actually did get because that was what I meant when I said repeated sync. Because we have a repeated eigenvalue, but the eigenvalue is negative. But this is the case. So this is the case where we actually have an eigenbasis. So the geometric multiplicity is 2. Here, the geometric multiplicity is 1. So, great. So star source. So we actually wanted star source here. So star source. Star source would be like 2, 0, 0, 2. Okay. Improper node source, we got that one. And then zero system, we did do that one. Or wait. Okay, so we did. Does zero system mean that both eigenvalues are 0? It means something more than that, right? It means literally that the matrix is 0 and that every point is at equilibrium. That's what it means. It means that the whole matrix is 0. So, zero system. Zero plus sync. How is that different from the nilpotent? Okay, so okay, so the nilpotent node is different because why? Oh, because we have What's an example of the matrix? Lambda equals -1. Okay, I'll be back in a second. That table is awesome. I love these pictures. So what are the eigenvalues for the last couple? So here we have right. So you get two eigenvectors, but one of them is 0. Right. Yeah, yeah. Dude, this table is the fucking dopest table ever. Where do I paste this in? Cool.txt. Oh, great. I like that it's in fucking LaTeX. Isn't that nice? I love it. Excuse me. Oh, that's very cool, though. All right, cool. So that is problem 1. We're not going to do the x of t and y of t cases, but all right. All right. I'm going to go fill up my water bottles. All right, let's do 2 first, actually. 2 seems like, because I want to do one of the easy ones before I do one of the hard ones. All right, so sketch the corresponding curve in the trace-determinant plane. So let's just get set up here. All right. So, problem 2. Y prime is equal to A minus 1, 2, 0. So the trace is equal to A, and the determinant is going to be equal to minus 2. Or wait, no, positive 2. So if we're drawing our trace-determinant plane, and we're thinking about the trace-determinant plane, this is going to be D, and this is T, and so we're like right about here, so we're going to be able to go along here, okay? So that means that the behavior we're going to expect, so here we're going to get a repeated root, here we're going to get a center. This is a spiral source, and this is, we're going to get, here I think we get 2 positive, real, distinct eigenvalues. So I think here we're going to get a source. So I think if we're going to go from like left to right, we start with a sink here. Then we get a what do we call it? A repeated sink, which is like which looks like repeated sink looks like this. Stuff like that. So then we're going to get that. Then we're going to go to a spiral sink where we so into this where we get no real eigenvalues, but we're going to get like a stuff like that, where this is going this way into the abyss. And then we're going to get a center, and I don't know if it's clockwise or what, but we just draw it like that. And then finally we get a another repeated root. What's the difference between these repeated roots? That this one is a source. So then we're going to get a, let's say that like this is the eigenvalue. Then we're going to get like, but eventually they become tangent. And then finally we get like boom, 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 boom. And this will be like boom. All right, so that is the whole progression of problem 2. Let's see, are we supposed to do something else? Sketch the corresponding curve in the trace-determinant plane. In a brief essay, discuss different types of behaviors exhibited by the system. Identify the values of A where the type of system changes. Okay, so we didn't do part C, so let's do part C. All right, so when t squared is equal to 4d, we're gonna get some issues, or we're gonna get some changes. We're also gonna get a change here, so we're gonna get 1, 2, 3 bifurcations. So the first bifurcation is gonna be when a squared equals 4 times 2, because this is 2. So this is going to be a is equal to plus or minus square root of 8, which is equal to what? 2 root 2? All right, so this is 2 of them. Then we're also going to get it where a is equal to 0. So these are the 3 bifurcation values. All right, let's see if we can do problem 3. Okay, problem 3 is y prime is equal to a squared plus a, 1, and a. This has gone up in difficulty significantly, bro. All right, so the trace is equal to 2a, and d is going to be equal to a squared minus a squared plus a is equal to minus a. Okay, so we're going to be plotting the curve, so let's just do our... So we have the curve 2a minus a. So is that not going to be just the vector like 2 minus 1? So if we went like 1, 2, minus 1, draw this line. So I think that's the curve. This is the 2 minus 1 curve. Okay, so we need to now, so what is this going to do? This is going to be a so we're going to go from sync with the real values to our what do we call it? Repeated sync. So one eigenvalue with geometric multiplicity 1. Then we're going to go to spiral sync. Then we're going to go to, what is this case? Is this case ambiguous when t equals d equals 0? What does that mean? That means that a plus d equals 0 and ad minus bc equals 0. But does that imply that a is equal to 0, 0, 0, 0? I don't think so. I think it can be, there's, because in our chart, there's this, but I think that this one, oh shit, this, I don't want to scroll up. We'll just wait for it to make it. Okay, so we're talking about these two. So interestingly, so in the trace det plane, the 0, 0 point is actually ambiguous in the sense that, so wait, nilpotent node looks like what? That's this one. We have an eigenvector of equilibrium points. Okay, so then we don't actually know. This could just be double. This is just 0, 0. So could be case 14 or A equals 0. Right. And then finally, what do we go to? So then we go to, after that, we're going to go to here, which is a saddle, right? So this is where t is less than 0. Or no, d is less than 0. And t is greater than 0. So when d is less, so then we're going to have t plus or minus square root of t squared minus 4d over 2. So this is going to be plus, and this is going to be plus. So then we're going to have, wait, is that right? Oh, but t square root of t squared minus 4d is going to be greater than t. So we have one real, or one positive, one negative. So yeah, we got a saddle. All right, so this is that. Then what did we need to do? We needed to figure out what the bifurcation values are. Okay, so we're trying to figure out when t squared is equal to 4d. So that means that 4a squared is equal to minus 4a. So this cancels with this, and this cancels with this, and we get a equals minus 1. Then we get a equals 0. All right, let's double check our answers, because these are new for me. I haven't done these really. So, oh, there we go. 1, 2, 3. They didn't talk about the 0 case, but that's kind of interesting that they didn't talk about the 0 case. So we got a real sink, repeated negative eigenvalue, spiral sink, repeated eigenvalues, and then saddle. Oh, they also showed the A values. I didn't show the A values. And then you get bifurcations at 0 and minus 1. Yep. Nice. That's cool, man. I love this stuff. This stuff is fun. Oops. All right. We can just move on to 5 now. I love these pictures. I love the geometry. I feel like I'm definitely more excited about geometry than the algebra and all that. Okay, so DE 3.7. All right. Problem 5. Y prime is equal to a square root of 1 minus a squared, 1, and 0. Okay, and they're saying plot this for minus 1 less than or equal to a less than or equal to 1. All right, so the first thing that we want to do is we want to find the trace. The trace is going to be equal to a. And the determinant, d, is going to be equal to minus square root of 1 minus a squared. Interesting. Wait, so we're going to get a curve. We're going to get our curve a minus square root of 1 minus a squared. You know what's funny is how much notation can impact your thoughts. Like if I just change this to be like, so this is going to be the x, and this is going to be the y. So if we did y, so f of x is equal to minus square root of 1 minus x squared. So if x is minus 1, if x is minus 1, then our trace is going to be like right here. So let's say this is minus 1. And this is going to be 1. Then we're going to get 0, right? So it's going to be here. And then when this is 0, wait, that's when this is D and this is T. When T is 0, we're going to get minus 1. So yeah, so I think I did kind of cheat because I kind of saw the answer, but it's like this. Terrible picture. So this is just going to go from, and then if we have our, what is this called? Repeated root parabola. So what happens at this boundary, actually? That's kind of a good question. This is when the determinant is 0. So we're going to have t plus or minus the square root of t squared over 2. So we're going to get, oh, so we have a 0 eigenvalues here. Is that right? So this is going to be these are the eigenvalues. These are lambda. So we're going to get t and 0. So yeah, so we're going to get a so we're going to go from having, what is t going to be? X a is minus 1 here, right? So t is negative. And if t is if the trace is negative, then we're going to have lambda equals like minus 1 and 0. So we're going to have like a type of thing where, wait, hold on. Is that right? Oh, you know what it is? No, I'm wrong. When 0 is an eigenvalue, we're gonna get like we're gonna get something like this. We're gonna get like this. We have this line, and then we have another line. Let's, yeah, sure. It doesn't have to be perpendicular, but then all the trajectories come in parallel to that in like this. Something like that. Okay, but so that's at this point. That's right there. And then here it's going to be going away from it. But then otherwise we're going to get a saddle. So how does this turn into? This turns into, I think it just, maybe it adds to this direction. So wait, let me not do that. So then it turns into something like this. Let's just do it on one axis. But then I think it's going to be like, so a typical saddle. And then it's going to go back into this type of thing where we like run away from one of the eigenvectors. So that's what I think. Let's see if I'm right. Okay, so we have a saddle. But it doesn't explain this. 1, 0 eigenvalue. Saddle. Oh, yeah, okay, okay, yeah. And then we have a saddle in between. Okay, great. Yeah, and then the bifurcations are at. All right. Good stuff, man. All right, so let's go to problem 7. This one looks fun. I actually like these problems. These problems are pretty cool because you get to draw a lot of pictures and you don't have to do a lot of algebra. That's the best, when you don't have to do a lot of algebra, but you get to. All right, so y prime equals a1 y. All right, so t is equal to 2a, d is equal to a squared minus a. You got your calculus midterm tomorrow? Good luck, bro. So this is equal to a times a minus 1. Okay, so what do we need to figure out? First, we want to plot what this curve even looks like. So we have this curve 2a, a squared minus a. So this should be this. Is this equal to a squared? I think it's the same curve, right? I think you can scale a curve and it's fine. So then we're going to draw our okay. So what does f of x equal to 1/2 a squared minus a look like? What does that plot look like? Let's just maybe we'll just plot some points. So for like -2, we know there's a 0 at 1 and -1. Or at 0 and -1. or 0 and 1. Sorry, so here's a 0, but this is 1/2. So we're going to get 1/2 times a minus 1. No, yeah, so we're still going to get our zeros at 1 and 0. So here and here are our zeros of a, which is consequently our zeros of t. And this is the trace, and this is the determinant. Luckily, they gave us ones where we don't have a crazy parametric curve in here. Because if we had a crazy parametric curve, I honestly don't know how I'd do it. So then I think that we're going to get a plot or something that looks like this, right? And its minimum value, if we did 1/2 a squared minus 1/2 a, we took the derivative, we would get a minus 1/2. So a at 1/2 is a minimum. So this is 1/2. So this is going to be the graph of a in the trace determinant plane. So this is the curve. And I honestly can't tell if this curve is t squared minus 4d. So t squared minus 4d is going to be a squared minus 4. So it's going to be 2 because that's going to cancel with that too. 2 a squared minus a. So if we set that equal, a squared minus 2a squared minus a. Wait. Something's wrong. This can't be right. Because this would be minus a squared minus a, but that doesn't make sense because it's an upward facing parabola and it has a 0. Am I sure I wrote this down right? Oh, let me check. Yeah, that's the right matrix. Because if you were to plot y is equal to minus x squared minus x, if you just go to Desmos and do that, it would look like a downward facing parabola, but it's definitely not. So I'm trying to plot, let's just try to plot the trace determinant. Wait, so wait, what is that? That is the... That is the curve of the trace and the determinant. But what we need is now t squared, so 4t squared. And then this is going to be 4. What? Oh, I was also curious. If I do this, so they're not the same parametric curve. You can't just do that. So that was already mistake number 1. All right, how do you do this one? This one's hard. That is so annoying. Okay. Why do they say delta is that? Delta is not... They're just calling delta the determinant, right? And the dashed parabola is the discriminant boundary. Wait, I was right, though. Wait, was I right, or did ChatGPT make the same mistake as me? Because this curve... Actually, parametric curves are kind of weird. What? Oh, no, it does say 0, 2, 0. Oh, this is 2, 0, but A equals 1. Okay. So, what I'm wondering, though, is that... But does it cross again? Like, does it cross, like, way out there? I feel like it does. So we actually got the right graph. I just didn't, I actually did get the right graph. So the graphs only meet at a equals 0. Okay, cool. All right. So that was 7. I'm not going to explain the behavior. The behavior went from like a spiral sink to 00 to a saddle and then to a source. Let's see. Is that what it said? It says we get a spiral sink, a nilpotent node. It even went so far as to note that it's a nilpotent node. I just said that the eigenvalues are both 0. Then saddle and then source. Easy. And then wait, when a is greater than, oh yeah, source. Oh yeah, no, oh shoot. Yeah, and we need that transition. So this is a repelling, so this is where the matrix has a non-zero null space. Okay. All right, wait, did I want to do number 8? I think I did want to do number 8. Oh yeah, this one's crazy, bro. This one's crazy. Consider the 2-parameter family of linear systems. In the AB plane. Okay, all right, so let's hop on my freaking pad of paper. Problem 8. Y prime is equal to A, what was the matrix? 1, B, 1. Okay, so we got the determinant and the trace. Now we want to make a thing like this. A, B, and we're trying to figure out what do I do with this information? I have no idea what to do with this information. A minus 1 squared is equal to minus 4b. If I square root, or wait, hold on. We can do b is equal to minus 1/4 a minus 1 squared. Okay, so sometimes just changing the y and x makes my brain a little bit more comfortable. So we want to plot this curve because what this curve represents is the repeated root parabola. So all right, let's just say if x is 0, or let's say, okay, at x equal to 0, we get 1 times minus 1/4. So we're going to be like, 1 is right here, maybe minus 1/4 is right here. So we're going to be like right there. All right, let's try to find the zeros. So if x equals 1, then this is going to go to 0, and this is going to go to 0. So x equal to, oh wait, this was x equal to 0. What am I talking about? X equal to 0 gives us this point. X equal to 1 is going to give us this point. So we should get kind of like a thing like this. And so if if t squared is greater than 4d, will we be above this graph or below this graph? So t squared is the all right, so let's just take like 0, 0. So 0, if a is 0, b is 0, then t squared, so at 0, 0, t squared is greater than 4d. So what I think that means is that all up here, this whole area is going to have real eigenvalues above this curve. I hope I'm right, but I feel like that makes sense. Wait, what is the actual problem? The problem says, identify all regions where this system possesses a saddle, a sink, a spiral sink, and so on. Okay. So here we have, so this is the repeated roots. So let's take like, oh my gosh, this problem is tough. All right, so let's take like a equal to -1, b equal to, or no, a equal to 0, b equal to -1. Then our matrix is going to be 0, 1, -1, 1. Which gives us, so that's going to be this point. And we're going to have a trace of 1 and a determinant of 1. So t squared is less than 4d. So here, I think it's, the trace is positive. So wait, actually, I'm not so sure that we have real eigenvalues up here. But I am certain that if we have all points on this curve, if we plug, so this graph gives us, if we plug in a point for x, we'll get a point for y such that we have a repeated eigenvalue. So if we just plugs in like x equals 2, x equals 2, then we're going to get y equals -1/4. Oh, wait. Oh, wait. This, because I did this all wrong. This is like this. Isn't it? I think this is actually like this, because... Oh, wait. Is it like this? Maybe like that. No, but it has zeros. Wait, does it have zeros? Yeah, if x equals 0, if x equals 1, then y equals 0. Oh, so is it like this? Oh, it's like that. It has one root. It's like that. Okay, that took us a lot of tries. Took us way too many tries. But so this, okay, so this is the right one. And this is at 1. It's a downward facing parabola with a single root. And so this should be basically, if I give you a point on x and you find the point on y for this curve, then we will get a case where so let's just try it again. So x equals 2 gives us y equals minus 1/4. Then if we compute the trace, so we're going to get a plus 1 squared equal to, and this is going to be 8 because it's 4a minus 4 times minus 1/4. So this is going to be plus 1, 8 plus 1, and this is going to be 2 plus 1 squared, 9 equals 9. So indeed, this curve tells us where the repeated root parabola is for these parameters. Now, if we take 0, 0, let's do 0, 0 again. So 0, 0, we got 1 is greater than, so t squared is greater than 4d for 0, 0. So this means that we should have real eigenvalues here. Which is cool. So then wait, what I want to know now is, let's say like, because our typical trace determinant graph is like t, d, and then we have this parabola like this. And we want to know where d is equal to 0. So to solve for d equal to 0, d equal to 0, we have a minus b equals 0. So if a equals b, so we're going to have this line here, I guess. And this line is the line where the determinant d equals 0. And then similarly, for the trace equal to 0, we have t equal to 0, we get a plus 1 is equal to 0. So a is equal to minus 1. So then we're going to have like, wait, this is a and this is b. So if a is equal to minus 1, then we're going to have like a line like this. So this is the a minus 1 graph. And it's, I don't know if these meet. Do these meet? We'd have to plug in a minus b is equal to this curve, which is a plus 1 squared minus 4a minus 4, or plus 4b. And then we have to solve for this and then figure out what the zeros are. And I think that there actually might be 2 zeros or 2 solutions. I think so. It might actually like even though this goes through 0, it could be that this like comes out around like this. I don't know how you're supposed to do this quickly. All right, so we spent enough time on that. Let's just ask ChatGPT now. I want to see how this thing handles it, because that problem is going to take forever if we're going to try to figure that out. What other problems are there on here? 9. All right, I feel like we did a good amount of problems. I feel like I know how to do the categories of problems. Oh, shit. Look at that. That's such a good plot, man. Dude, ChatGPT can make some of the coolest freaking plots ever. All right, so indeed there was only one, which I don't know if that like makes sense for some deeper reason. Dude, this plot is so sick, man. This plot is so cool. That's so freaking cool. I love that, dude. All right, so we get the saddle above this. Wait, so when I said that there were real eigenvalues, let's see, that's a source, that's a sink. Okay, so I was actually right. All of these parts above the parabola are going to give you real eigenvalues. And then what's at this point? That point's the point where you have 2 0 eigenvalues, I'm guessing. -1, -1. If A equals -1, then the trace is 0. And B is -1, too. So you're going to get... Okay, so yeah. So this is the point where the trace is equal to the determinant, which is equal to 0. That is such a cool plot. Okay. We're definitely going to get a question like this on our quiz, man. All right, I think that's going to be it for this section. I don't think I'm going to do any more. I said I was going to do some more, but let's see. Spent 2 hours on this section. I feel like that's pretty good. I'll probably do some review over the weekend. Peace out.